Hello everyone, my name is Sathesh Santhanasamy and my metric number is B0822100003. Welcome to our presentation on second order system, which is electric power steering system. An EPS system represents a significant advancement in automotive steering technology, replacing traditional hydraulic system with an electrically driven mechanism to assist the driver. EPS system consists of key components such as steering wheel, torque sensor, electric motor, controller, and steering rack, which work in harmony to provide precise and adaptive steering assistance. In control theory, the EPS can be modeled as a second-order system, characterized by its natural frequency and damping ratio. This model helps in understanding the dynamical response of steering system, where the natural frequency influences the speed of response and the damping ratio affect the nature of the response, ranging from oscillatory to critically damped. By analyzing the EPS through this framework, engineers can optimize parameters to ensure a balance between responsive and stability, enhancing both the driving experience and vehicle safety. In this report, we analyze the electric power steering systems dynamics, control mechanisms, block diagram representations, system modeling, performance metric calculation, MATLAB simulation and validation, state space representation, stability analysis, and steady state error. Question 1. Explain what the application is all about. The electric power steering system is all about a modern vehicle to assist the driver in steering the vehicle. Unlike traditional hydraulic power steering system, EPS use an electric motor to provide steering assistance. This system improves fuel efficiency as the electric motor only operates when steering assistance is needed, unlike hydraulic systems that run continuously. The second question is, explain where the control is being used. The control in the electric power steering system is used to adjust the level of steering assistance provided by the electric motor. This adjustment is based on feedback from various sensors such as torque sensor, vehicle speed sensor, and position sensor. These sensors monitor the driver's input and the vehicle's dynamic to ensure that the steering effort is appropriate for different driving conditions. For instance, more assistance is provided at lower speed for easier controlling, such as during parking or low-speed city driving, and less assistance is provided at higher speed for better vehicle stability and control on highways.
Good morning. My name is GOVINNATH, son of PONNUSAMY. My metric number is B0822210085, and I'm explaining about question D. Model the system to get the system transfer function. The system we choose is a EPS system. The EPS system can be modeled as a second order system. The dynamic can be represented by the following transfer function. GS equals to theta out theta in equals to K per JS power of 2 plus BS plus K, where J is the moment of inertia of the steering mechanism, B is the damping coefficient, K is the control gain representing the motor assistance. Assuming the following parameter value, J equals to 0.05 kilogram meter square and B is 0.1 Newton meter second per radius and K is equivalent to 1 Newton meter. The transfer function becomes as like GS equals to 1 per 0.05 S power of 2 plus 0.1 S plus 1. And we go on to our next slide. In this video, we will go over the key characteristic of dynamic system. First, we have calculated the natural frequency omega n to be approximately 4.47 radians per second. This indicates how fast the system oscillates without any damping. Next, the damping ratio zeta is found to be around 0.224. This value tells us about our system is under damp, meaning it will oscillate before eventually coming to rest. Moving on to the peak time, TP, it is approximately 0.72 seconds. This is the time it takes for the system to reach its maximum value after being disturbed. The setting time, TS, which is the time required for the system to settle within a certain percentage of its final value, is roughly 4 seconds. Lastly, we have the percentage overshoot, which is about 48.5%, 5%. This metric shows the extent to which the system exceeds its final state value during its transient response. To summarize about the all value got in above, which is natural frequency equivalent to 4.47 radian per second, damping ratio is equivalent to 0.224, peak time is equivalent to 0.72 seconds, settling time is equivalent to 4 seconds, percentage overshoot is equivalent to 48.5%. This parameter helps us understand, predict how it will respond to changes over time. That's all. We will move on to our next slide. And the next slide we move on is our simulation which is created by using MATLAB. And we will show you our block diagram. We use a step input, a transfer function, and a scope. The transfer function which got a function which is 1 per 0.05 s power of 2 plus 0.1 s plus 1. And throughout the experiment we get the graph of under them. And we move on to our next question. So peak time, settling time, and percent overtake our graph obtained and compare the calculated value. And throughout the simulation result we get our values. We get our value, overshoot values, our time, our peak time, peak value. After running the simulation, the system response graph will show the peak time, settling time, and percent overshoot. This value should be compared with the calculated value. And the peak time we calculated, we get 0.73 second. And while we simulate using our MATLAB, we get 0.721 second. The second one, settling time, TS, when we calculated, we get the calculated value of 4 seconds, while in the simulator it didn't show up. And next one, we move on to our percent overshoot, and the calculation we get 48.5%, while we simulate we get 48.507%. Next thing, we move on to our how to convert the system transfer function to the state space representation. First of all, we normalize the coefficient of denominator polynomial so that coefficient of s power of 2 is equivalent to 1. So we using our transfer function 1 per 0.05 s power of 2 plus 0.1 s plus 1. To get our denominator polynomial become 1, we have to divide all term in the denominator by 0.05, and we get the normal transfer function which is 1 per s power of 2 plus s 2s plus 20. And we have to identify the coefficient of denominator polynomial which is as, and as equal to our denominator polynomial which is s power of 2 plus 2s plus 20. The coefficients are a2 equivalent to 1, a1 equivalent to 2, a0 equivalent to 20. The state space representing matrix are state matrix A, which is A equal to matrix 0, 1, negative AO, negative A1. Substitute A0 equal to 20 and A1 equal to 2, and we get our state matrix which is 0, 1, negative 20, negative 2. For our input matrix, it will become B equal to 0 or 0, 1. And the output matrix C will become C equal to 1, 0. And the feedback through matrix D will become D. And the summary of state space representing the state space given transfer function which will be 1 over 0.05 s power of 2 plus 0.1 s plus 1. We can simulate this as like this: x equivalent to ax plus bu, y equivalent to cx plus du. And this is our result we get throughout the state space representation. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is AFZAL HAIRIE bin ABDUL HALIM. My metric number is V082210227, and I will continue to explain the electric power steering system, which is EPS. Okay, I will continue to explain the stability of the system. The real part of eigenvalues is lambda 1 equal to negative 1 I square root of 19, and lambda 2 is equal to negative 1 minus I square root of 19. The value of this equation is negative, indicating that the system is stable. A negative real part means that perturbations will decay over time, bringing the system back to equilibrium. The imaginary part is plus minus I square root 19, signifies oscillatory behavior typical of underdamped second-order system. This underdamped nature leads to transient oscillation, but since the real part is negative, this oscillation will eventually die out. So next, I will explain the how to calculate the steady state error for step input, ramp input, and parabolic input. So for the three of this input, they have different steady state error. For example, for the step input, we use the equation of Rs equal to 1 over S. So the error of steady state, we put it as limit S equal S to 0, which is 1 over 1 plus GS times with 1 over S. GS, the value of GS we take from the above, which is 1 over S square plus 2S plus 20. So we just put in the equation, and after the calculation, we get the steady state error is equal to 0. So the steady state error for the step input is 0. Next, same also for the ramp input. For the ramp input, which is we use the equation Rs equal to 1 over S square. So after put the value of the GS in the equation, we get the steady state error equal to infinity. So the steady state error for the ramp input is infinity. So for the parabolic input, we use the equation of Rs equal to 1 over S cube. So after we insert the value of GS, we calculate, and steady state error, we get the infinity also. So the steady state error for the parabolic input is infinity. Next, about discussion. The detailed analysis of the EPS system transient response and stability provides crucial insights into its performance. The underdamped nature of the system, as indicated by a damping ratio of 0.224, results in noticeable oscillation and overshoot in step response. This behavior is typical for second-order system and impacts key performance metrics such as peak time, settling time, and percent overshoot. The stability analysis using Nyquist's criteria, bot plots, and root locus plots highlighted the robustness of the EPS system under varying conditions. These techniques are essential for identifying and mitigating potential stability issues, ensuring the EPS system can maintain controlled behavior in real-world application. MATLAB simulations play a vital role in validating the theoretical models, providing a visual quantitative understanding of the EPS system dynamics. The simulation confirm the system performance metrics and stability, demonstrating the efficiency of the modeling and analysis approach. In summary, the integration of theoretical analysis and MATLAB simulations offers a comprehensive framework for understanding and optimizing EPS system, contributing to the advancement of automotive steering technologies. So next, the conclusion. This report presents a comprehensive analysis of a second-order electrical power system, which is EPS system, focusing on its dynamic behavior and performance characteristic. The mathematical model, which incorporates the motor's inertia, damping coefficient, and control gain, accurately captures the fundamental dynamics of contemporary EPS system. Key performance metrics including the natural frequency 4.47 radian per second, damping ratio of 0.224, the peak time 0.73 second, settling time 4 second, and percent overshoot, which is 16.5%. We derive from the model a true transient response analysis highlighted the system ability to achieve desired steering position and velocities with acceptable precision and speed, despite the inherent oscillation due to underdamping. The stability analysis utilizing techniques such as Nyquist's criteria, bot plots, and root locus provided critical insight into the system robustness. Overall, this report underscores the importance of understanding the transient response and stability of EPS system. By combining theoretical insight with practical simulations, we have established a solid foundation for optimizing EPS system. Thereby, contributing to the advancement of automotive steering technologies. The findings and methodologies presented in this report provide valuable guidance for future research and development in the field of electric power system. So that's all from me. Thank you.